always good to see you and see you grow and be back here at Korea University. So today I will be talking about reconfigurable intelligent surfaces. This is a topic that a lot of people have been looking at in the past few years. And here what I want to look at is some new architectures that we'll call beyond diagonal reconfigurable intelligent surfaces. And I want to show you what's the benefit of those architectures and how it works. So this is joint work with several people, including Shampoo. Shampoo was a postdoc at Imperial in my lab, and now he's at HKUST. Matteo and Hongyu are two PhD students in my lab. And then we have Ross Merge at HKUST, Laios Hanzo and Mohamed El-Ajjar at Southampton, with whom we have also collaborated on some of those topics. So, so what I will be talking about today is the following. I will briefly motivate the problem of those beyond diagonal RIS. I will then try to, you will see the talk brings a lot of tools for microwave theory. And so I will look at some model of those RIS using what is called scattering parameters. And then we look at different architectures of those beyond diagonal RIS using different structures and different modes. And I will explain what that means exactly. And then I will conclude. So you're all familiar with reconfigurable intelligent surfaces, or RIS. This is also called as intelligence reflecting surfaces. Lots of groups in the world who have made an outstanding contribution in this area. And the whole benefit, essentially, what is a RIS is essentially a large number of reconfigurable elements that you can place within the environment. And each of those elements essentially can adjust a phase shift and therefore change the incident wave into a reflected wave, and essentially engineer the channels and reconfigure the channels as a function of the channel state information, for instance, and the objective function that we want to maximize. And all those elements, they work together in the sense that what you want to do is maybe interfere constructively at some point in space or destructively in some other point in space. And the advantage of RIS is that it's nearly passive, so it has a very low power consumption. It's relatively low cost. It doesn't generate any thermal noise, and there is no self-interference. This is why it's very attractive for energy efficient and spectral efficient wireless communications, but also other wireless applications like wireless power or wireless sensing. Right, so there's been a lot of work on looking at those RIS for different applications and looking at the system level optimization. And then here in this talk, we'll not look at this. We'll look at two things. The first thing is, how can we model those RIS or IRS? I will mainly use the term RIS, more from a physical perspective. And there might be a different model in the literature, but the one we look at is really inspired by microwave theory. And the second objective is to look at new architectures, and this really the main focus of this talk, those beyond diagonal RIS. So you will see this classification that will come up a few times in these talks, and what it means is that you have RIS, and you can take different branches depending on the architectures that we'll be looking at. So the left branch here is something that we'll see. This is the conventional RIS. And typically it uses a diagonal matrix, and you will see what it means by diagonal matrix in a minute. And you have this whole set of branches here within these dashed lines. Is really going to be the focus of these talks, where we're going to depart from diagonal matrices and explore different structure of matrices, block diagonal, non-diagonal matrices, and see what's the benefit of this and how we can obtain such matrices. So let's dive into some basics first of scattering parameters. So remember from your microwave theory course that if you have a transmission lines like here that is terminated by a load, essentially you have an incident voltage wave and you have a reflected wave, and the reflected wave depends on the impedance loads and the characteristic impedance of the transmission line. And so you have reflection coefficients whenever the load and the characteristic impedance actually not equal with each other. And so you can generalize this into a case where you have n-port networks. So now here in these examples, I have 5 port networks here. And essentially you have an incident wave in one of those ports that will be reflected by the ports that will be reflected back. But this incident wave, part of the energy will also flow through other ports. And so how can you relate the incident wave of each of those ports with the reflected wave? Is through this scattering matrix that relates the reflected wave voltage to the incident wave voltage at each of those ports. Right, so how can we use this in the context of RIS? So imagine now you have systems where you have a transmitter with a certain number of antennas, you have a receiver with a certain number of antennas, and then you have a RIS in between. And you can have NT antennas here and R antennas here and NI antennas at the RIS. And so in total, you have a total number of antennas that is equal to capital N. Here's the sum of all those antennas. And you can take all those antennas and essentially now imagine that this is actually a gigantic N-port network. And so you can actually model this N-port network using the scattering matrix, saying that the incident wave at each of those ports will be connected to the reflected wave at each of those ports, at the transmitter, at the RIS, and at the receiver, and reflected wave inside that N-port network. Then the next thing you can do, you can model the transmitter, the receiver, and the IRS. And so how you do that, you say, well, I have here every time an incident wave inside this N-port networks, and I have a reflected wave. Well, those two are also related to what you see on the left side from this network, which is the transmitter. And you can say that this wave A here, the incident wave to the N-port network, is related to the voltage source here that you have here, and the reflected wave coming from the N-port networks. And so you have a relationship between, against this incident wave and reflected wave from what's happening at the transmitter side. At the receiver side, same thing. A and B are related to the scattering matrix that you have at the load. And so you have a scattering matrix at the transmitter, you have a scattering matrix at the receiver, and that would also relate the incident wave and the reflected wave. And finally, and this is the very important part in RIS, is that those A and those B's, incident and reflected wave, are actually connected through also a scattering matrix that is here denoted as theta. And the difference between theta and those gamma is that those gamma are typically something that is fixed that you don't reconfigure. But in RIS, essentially, this theta is something you can really reconfigure as a function of the channels. And that's the whole purpose of this reconfigurable scattering matrix, is to be able to change the environment as a function of this, the parameter that you set here. Right. So if you take those different equations, so these ones here, this matrix, and those 3 bits here, and you collect them all together into this equation, what you can do is now you can compute the relationship between the voltage at the transmitter and the voltage at the receiver. So what will be the voltage at the transmitter and the voltage at the receiver? It will be the sum of the incident wave and the reflected wave at each of those ports. And I can now find a relationship between the receive voltage and transmit voltage, and you can show that actually those two are related through a channel matrix H, or matrix H, that is a function of many different parameters here, but in particular is a function of this theta, the scattering matrix of the RIS, that is hidden within this channel matrix H. Now, you don't see it because this H is essentially a nonlinear relationship of the scattering matrix H. But the interesting bit with this model is that this equation here would capture any mutual coupling that you have among any of those ports and any impedance mismatch that you have at any of those ports. But it's quite complicated to use. So what you can do, you can say, well, what if I have perfect matching at each of the ports and I have no mutual coupling? So what's happening then is that some element in those matrices get equal to 0, And this channel matrix H that was relatively complicated, where you don't see the theta appearing clearly, suddenly simplifies into something where we're much more familiar with, which is essentially saying that you have a scattering matrix that will model the transmitter to the receiver. That's a kind of direct link. And then we have a scattering matrix from a transmitter to the IRS, the RIS scattering matrix, and then the scattering matrix from the IRS to the receiver. And so you can think of those scattering matrix here S as essentially a channel matrix in communication engineering terminology. And so this is interesting. It says that essentially, if you want to have a model that really capture the mutual couplings and the impedance mismatch, well, be careful. This would have some limitations because this does not capture this, and you would have to use a more complicated models that you have here. If you can afford to really assume you have perfect matching and no mutual coupling, then you can indeed use this more intuitive model. Now, what we're going to do next is try to understand this theta architecture. And so essentially, what do we put in this green box here in order to relate those incident wave and reflected wave at the RIS level? Right, so we look at first architecture based on block diagonal and reflective mode. So what does that mean, reflective mode? It means that the transmitter and the receiver are on the same side of the RS. So the wave will actually bounce against the RS and will be reflected in a certain directions. That is the direction of interest where this receiver is located. So we can come up with a few architectures, and the classical architectures that you use here to connect those different essentially antenna elements is to use what we call here single connected architecture. And single connected, I have an example here, it means that each port of the RS is directly connected to a load with its own impedance. And what you do is essentially control the value of this impedance in order to control the phase shift of each of those elements. And if you assume that you have a lossless systems, what you're going to have is actually a scattering matrix that is now equal to a diagonal matrix. And the diagonal comes from the fact that each of those elements is not connected to each other. So port 1 is not connected to port 2, not connected to port 3, and not connected to port 4. And so from this, you have Ni elements or Ni loads to control, and that enables you to have this diagonal scattering matrix. Now, if you assume it's lossless, you see the entries have unit modulus. So it's not larger than 1 because you don't do active amplifying. And it's not smaller than 1 because we assume we have a lossless system. But what this does, essentially, will control the phase of the impinging waves, and will only be able to control the phase of each of those elements. Now you can have another architecture, which is here, what we call fully connected. And so you have 4 ports in your RIS, but any port is always connected to all other ports. So port 1 has its own impedance, but is also connected to port 2, port 3, and port 4. And so now you have more loads or more impedance to design. You have a number that scales like with the square of the number of elements, the number of RIS elements. And you have an equivalent constraint that says that instead of having the elements here, diagonal element that is equal to 1, now we have a constraint on the scattering matrix that has to be unitary. This unitary comes from this lossless property. Essentially, it says that you have energy conservation and you don't lose energy when you have the interaction between the waves and the scattering surface. And you can have another constraint that says that here this theta matrix is symmetric. And this comes from the fact that if you want to simplify your circuits, you may want to use reciprocal impedance networks. For RF people, it makes things a bit easier. So the benefit of this is that now your theta is not diagonal anymore. Your theta will be a full matrix. And this full matrix, the benefit is that you will not be able to only control the phase of each of those elements, you can also control the amplitudes. So that's the first benefit of this architecture. I will show you how this translates into power gain in a minute. Right. Now, one drawback of this is that if you increase the number of elements here, well, it grows very quickly and you have many elements or many impedance to design and optimize. So what you can do, you can come up with a group connected architectures. Let's say that, for instance, here I have 8 ports, so 8 RIS elements, but I divide them into 4 groups and I only pair them, I only link them in group of 2, right? So by doing this, port 1 and port 2, they will be able within that group to control the phase and the amplitude, but between groups, they will be disconnected. And this would lead to actually a block diagonal structure of your RIS scattering matrix, where the number of blocks you have is essentially the number of groups that you have in this RIS. And you can adjust the number of elements you have in the group. So if you have 8 elements, you could have 2 groups of 4 or 4 groups of 2, for instance. Right. And so you have similar conditions here, constraints on the unitary property that would be for each of those blocks and on the symmetry. Right. So now you have a model that captures all the non-idealities. You have a model that actually is simpler, that is based on perfect matching and no mutual coupling. And now you have 3 architectures. The first one is single connected. That's a conventional one that the literature has been using extensively. And then you have these other architectures based on fully connected and group connected, which are particular instance of what we call beyond diagonal. Right, so this was essentially this first link here, this first branch that says you start with a block diagonal matrix and you use this only to reflect the wave. So the question we can ask ourselves is, what's the benefit in terms of the amount of power that is now reflected by this RIS? And so let's look at these simplified models where we assume we have perfect matching and no mutual coupling. And what we're interested in is really the power of this term here. So in other words, this quantity here. And what we can show, we can calculate this for different structure of this impedance network, whether it's single connected or fully connected. And you can find the theta that would be the optimal theta for the single connected and the fully connected. So in the single connected case, what essentially you can do, you can play on those phases in order to match the incident phase of the channels and the reflected phase. And this essentially acts as a form of equal gain combining, if you like, because you only place on the phase of the incident wave. You don't play on any magnitude. You cannot because of this constraint of this single connected RIS. Now, what you can do as well, you can compute the amount of power you would obtain where you have a fully connected RIS. And so what you can show is that the power of the single connected is essentially always smaller than the power of the fully connected RIS. And you have some conditions where actually those 2 powers are the same. So in other words, there are some conditions when single connected would give you the same amount of power as fully connected. And this happens whenever you have this kind of condition. So HIT is a channel vector between the transmitter and the IRS. And HRI is the channel vector between the IRS and the receiver. And whenever those elements of those 2 channels are trying in a scaled version of each other, where the scaling factor is alpha, then the performance of fully connected is the same as single connected. When do you get this kind of condition is whenever you have perfect line of sight. If you have a perfect line of sight from the transmitter to the IRS and the IRS to the receiver, then you have this condition is satisfied. And in that case, single connected and fully connected would give you the same performance. But if you have environments that is more closer to IID relay fading, then you're going to have different fading on each of those elements. And this is when the fully connected now start giving you a power gain. And you can think of this as the analogy with equal gain combining and maximum ratio combining. In communication, when you have different fading across different antennas, typically you want to use maximum ratio combining. When the fading is the same across all antennas, the equal gain combining is sufficient. Right, and so this translates into an increase of the average received power at the receiver. So here you have an example of the received power versus the number of elements that we have in this RIS. We have the red one is single connected, and then green one is when you have group connected of groups of size of 2. The blue one, the cyan, is group size of 4. and the dark blue is when you have a fully connected architecture. So as you increase the group size, essentially, you see that the performance increase, you deliver more power to the receiver because essentially all those elements are connected and they will be able to act more like a maximum ratio combiner. Right. So what you can show mathematically is that if you have relay fading, you have a power gain, you increase the amount of power between single connected and fully connected by 60% by having all those elements that are connected with each other. The drawback of this is that the number of elements that you have to design scales quadratically with the number of ports. And so group connected is an alternative in between that trade essentially complexity versus performance by saying you can still have a power gain, but you have a number of elements that increase just slightly compared to the single connected case. Right, so that's the second benefit. This being able to control the phase and the amplitude translate into a boosting of the received power. So one more thing you can do when you have this group connected architecture is that now you can decide how you group those elements together. And you can imagine that you can have different ways of grouping. The first way would be based on channel statistics. So you don't change the grouping on a per channel state information basis, but you change this whenever the statistics of the channel changes. And the second one is on a per realization basis. And you can have a correlated groupings and uncorrelated groupings. So imagine you have your RIS element like this here, and the antenna from the same color in red here, they're close to each other. Those elements are closer to each other. So typically they would experience correlated fading compared to antenna that are further apart from each other here. If you connect those red elements together, they would experience more uncorrelated fading. And so the propagation conditions are different for those two. And if you remember what I said before, I said that if you have more IID fading between elements, the MRC, also the fully connected, would help. And this is typically what happens here. If you have more uncorrelated fading, you better have a grouping that actually such that you connect elements that are further apart from each other. Optimal grouping is when you change on a per realization basis, the connection between the elements would actually change. Right, and this is what you can see here. This is a power gain, so it's the gain of the fully connected or the group connected versus the single connected, so the conventional one. And what you can show is that the uncorrelated groupings increase the power gain over the correlated groupings. This is what you see from those curves here. And the optimal grouping, that is here, the optimal groupings with actually a group size of 4 achieves the same performance as a fully connected. So if you have a group size of 4 in your IRS, but you're able to adjust the grouping between all those elements dynamically as a function of the channels, you will have the same performance as if you have a fully connected network. And so the grouping here, the dynamic grouping, helps you to essentially decrease the number of elements that have to be connected with each other, as you would have in a fully connected network. So the third benefit is because of this block diagonal structure, and you can actually now group elements together, and you can do this dynamically or semi-statically, and that helps you boosting the received power. Right. So far, assume that we have continuous impedance, so you can really optimize them fully. Now, in practice, you may have discrete impedance. So actually, those phase elements of this scattering matrix, typically, they would be quantized. And typically, when you have, or equivalently, when you have group connected, those theta will be connected to essentially an impedance, and the number of impedance that you have available doesn't come from a continuous space, it comes from a discrete code book. And so the question is, what's happening now if you have a discrete elements or discrete number of impedance in your available to design your scattering matrix? And so what we can do some form of unsupervised learning or k-means clustering or Lloyd algorithm to design this optimal this code book of scattering matrices. And what we can show is the following. This is the received power versus the group size. and we have 64 RIS elements. And in blue here, the dark blue is the upper bound. This is when you have fully connected and fully and continuous. There is no discretization. And so what you see is that you have different colors that tells you the number of bits that you have for each of those impedances. So if you have 1 bit, you have essentially 2 possible values of the impedance for each of those loads. As you increase the number of bits, the performance improves. That's quite natural. But what is more interesting is that as you increase the group size here on the x-axis, you see that actually the gap between 1 bit and the optimal one, the continuous one, decreases. And so, for instance, if you have groups of 16 or 32, you could have just 1 bit for each of those loads, and this 1 bit would give you performs almost the same as if you have a fully continuous, fully connected network. On the other hand, if you have a group size of 1, this is the same as having single connected, the traditional architecture. You would incur a loss if you have only 1 bit, and you would need to go to a larger number of bits in order to recover that loss. So what that enables you by having this architecture of block diagonal RIS or beyond diagonal RIS is it enables you to have fewer resolution bits for each of those impedances. Right. So another benefit is when you have a hybrid mode. So what is a hybrid mode? And this is actually the second branch in this beyond diagonal. This hybrid mode is the following: is when you want to use your RIS to reflect part of the energy, but you also want some part of the energy to travel through the RIS and go on the other side of the RIS. And so how can you do that? Well, the basic idea is simply you can take this group connected architectures that I showed you early on that was used for reflection only, where, for instance, I have 4 ports here, and those 4 ports would be used to reflect the wave. So you see the waves would be coming from the left side, would be reflected by all those 4 ports, and then directed back to a user on the left side of this RIS. Now, if you take this architecture, you don't change anything into the architecture, but what you do, you take those antenna, and instead of orientating them to the left, you take one of them and you orientate it to the right, right? And this is what you have here. You take the same circuit, but now those 2 antennas that actually in opposite directions. And so what's going to happen there is that you may have an incident wave coming here on the left side. It will be, part of it will be reflected from the antenna 1 here, and will actually maybe illuminate a user on the left side of this RIS. And part of it will go through and now illuminate a user on the right side of the RIS. So this is this hybrid modes that enables you a joint transmission or and reflections. And so that enables you essentially a coverage in front and at the back of the RIS. Now, we can now generalize this architecture by saying, imagine that we have a transmitter, we have multiple users on the left side, multiple users on the right sides, and now I have this RIS architecture where, in the same way as I had here, where I was pairing 2 users with antennas in opposite directions, now I have 2 M ports here. I have M antennas or M ports on the left side, M antennas on the right side. And every time I have at least within each of those, what is called cell here, I have 2 antennas that are connected to each other, so that the wave would come from the left side, would be reflected, or would travel through, and part of it will be forwarded. And you can model this as well, again, with a scattering matrix here. Instead of theta is this phi. These are 2m by 2m scattering matrix. And what you can do some analysis, you can based on some assumptions, and actually what's happening is the following. You are going to have a transmitter, you're going to have multiple users on the left and the right sides, and part of the scattering matrix phi here can be divided into different blocks. And some blocks, what they will do, well, they will tell you how much. The scattering matrix will tell you what comes from the transmitter will be reflected by the RIS and then back to the left side of this plane. And another block of the scattering matrix will tell you
how the waves will actually come from the transmitter and will propagate through the RIS, and then we illuminate the right side of the plane. And because of the structure because of this unitary constraint that we had in the RIS, we now have a relationship between the scattering matrix that is used for reflection, that I was calling phi 1, 1 here and phi 2, 1 here. Those two are essentially connected to each other, or you can recall them as phi r and phi t, just to imagine that actually one is for reflection and the other one is more for transmission. And those two are connected through this scattering, this unitary matrix properties that essentially says that you have energy conservation when you design your scattering matrix. Some of the energy will be reflected, some energy will be forwarded, but in between you will not lose any energy. That's what it says. And it's a hybrid mode because potentially you can design this phi r and this phi t such that you can adjust as a function of the users how much is reflected and how much is propagated through. Right, so now we can come up with architectures of what's going on within this RIS here, right? Or within this panel where you have RIS on one side and on the other sides. How are all those elements connected to each other? And you can think of multiple architectures. The first one, which is the simplest one, it says, well, I have each of those cells is made of two antennas, and those cells are completely independent from each other. They are disconnected from each other. And so what's going to happen then is that you're going to have a scattering matrix that will be used for reflection. That will be diagonal matrix because those cells are disconnected with each other. And I'm going to have a scattering matrix that will control the phase for the waves propagating through the RIS. And this one will be diagonal as well, simply because those antennas are disconnected with each other. Or I could have an architecture where I have those cells here. Within each cells, we have elements connected with each other in order to enable this hybrid mode. But among cells or between cells, I have connections as well. And so in that case, the phi r matrix is not diagonal anymore. Those phi r matrix now could be full matrices. And you can have something in between, like here, for instance, where you have 8 ports. And now you group this into you have 2 groups of 4 ports for each. And so in this case, I'm going to have, again, at the group level, I'm going to have these unitary constraints. And those scattering matrix on each of those groups for reflection and transmission would have a block diagonal structure. Right. So what we can do with this is now we have this single connected and group connected, and we can adjust also as a function of the mode that we want, whether we want to reflect more, or we want to let the energy go through, or we want to have something that is hybrid as a function of the load, the number of users we have on each side. You can adjust, and so you have a really hybrid mode that enables you more flexibility jointly with this single connected or fully connected or group connected architecture. And so you end up with an architecture here of this beyond diagonal RIS that enables you another benefit, which is an efficient and flexible hybrid mode where you can enable any of those 9 possibilities. So you can have the first case, it says is single connected reflective. So single connected reflective is when you have essentially all those elements here, those cells are disconnected with each other, and the energy or the loads are designed so that nothing goes through, but everything is reflected. And then you can have other variants where you have single connected, you have transmitting, all the energy goes through, you have hybrid, part of the energy goes in both sides, or you can have fully connected where actually all those cells are connected with each other, or you have something that is group connected. And that enables you to have dynamic configuration and flexibility in your design of the RIS architectures. And that gives you a performance benefit. So this is a multi-user MISO systems where we have 6 antennas at the transmitter. We have 6 users. We have 2 users on the left side of the RIS, 3 users on the right side of the RIS. And we have a number of RIS elements that increase here. And we have this for relay fading and vision fading. And what you can see is that for all those scenarios, the sum rate increases with the number of RIS elements that you have. This is obviously not surprising. What is more interesting is that if you have an architecture like here, the solid line, right? This is a hybrid fully connected RIS. So hybrid fully connected RIS is something like this, right? But you imagine now you have many more elements. So you can really have this hybrid mode where you can cover the left side and the right side of the space, and all those elements are connected with each other. And what you get is a performance enhancement in terms of sum rate that is now significantly larger over the other architecture that you can come up with. The classical architecture or conventional architecture is here. This is the single connected one. And you see the significant sum rate enhancement that you can achieve as a function of the elements that you have in this RIS. And if you have something that is hybrid, then you have performance that essentially falls in between. Right. So once we have this hybrid mode, now we can think about the next architecture, which is now a multi-sector. And this is the third branch here in this tree. And the multi-sector is the following. Imagine that now you have an architecture that enables you to reflect partially and transmit. The drawback of this is that you can actually, you have a beamwidth that actually still has to be quite wide in order to cover 180 degrees on each side. Now, what you could have is you can leverage this beyond diagonal RIS such that now you have an architecture where you have multiple sectors, and on each of those sectors, the antennas gain and beamwidth is designed such that it covers just a small part of the 360 degrees space. And so you have here an example here where you have essentially 6 sectors. And so each sectors really have a narrower beam pattern. And so if you make some assumptions, you can also calculate the channel matrix of a given users will be a function of a scattering matrix here. I here ignore the direct path for simplicity. But you end up with a scattering matrix here that we had before. I call it phi r and phi t when you had the hybrid mode. Here we're going to have a number of scattering matrices that is equal to the number of sectors that we have. And so imagine, for instance, that you have a transmitter. You have sector 1 here on this side, and I'm the transmitter. I'm forwarding energy towards this transmitter 1. So part of the energy will bounce back from this sector 1 if I have users around me, and part of the energy, this energy, reflected, will be captured by scattering matrix phi 1, and then the other sectors will have a scattering matrix phi L that will tell essentially how much energy and how those different elements work together in order to forward the energy towards one of the sectors. Right, and this is really what you can see here. Using a single connected, cell-wise single connected architecture. So imagine here that I look at the first row of these RIS architectures, just the first row, and I deploy it on this 2D plane. And what I'm doing, I'm taking one element of the sector 1 and I'm connecting it to the corresponding element of the other sectors. So I take this element here, this one, and I connect it to this one here, this one there, this one here, and so on. So all those one will actually be connected among each other, like a group connections as we had in the previous cases. And what this enables me to do, it enables me, if I have a transmitter, I transmit some energy into this element here. So that corresponds to this one here. And part of the energy will be reflected to those users, and part of the energy will flow through and will go to the corresponding element to eliminate the users on each of those sectors, and correspondingly for other sectors. And similarly, you can have another element here would be connected to this one and to this one and to this one and so on. And that would be represented by this green flow of energy. This one would be connected to this one here and to this one. And so the energy will flow through this RIS and could be dynamically controlled. So this is an example where you have what we call here cell-wise single connected, because each of those elements here is connected to other sectors, but those elements here are not connected among each other. So what you could do, but it's more complicated, is you can have a fully connected architectures where the connection goes across all elements within the sectors and all elements across sectors. That would have the full-blown flexibility in your RIS design. Right. So again, how would you design this kind of architecture here? Right. Imagine I have 4 sectors. Well, I take my group connected architectures of beyond diagonal RIS that I had early on. For instance, here I have 8 elements in 2 groups, and I was using this for reflections only. And what I do now, same as what we did in the hybrid modes, I take those 4 antennas, and now I bend each of those 4 antennas such that each of them would have a coverage on each of the 4 sectors. And so that's what we have here. Now, each of those 4 antennas would illuminate a different part of the space. And you would have to design the antenna again such that indeed you cover just pi over 2 every time. And so those different scattering matrix for each of those sectors would have to still satisfy these unitary constraints such that you have no loss of energy and you have energy conservation. And so what's the benefit of this is that as you increase the number of sectors, you have really very efficient full space coverage all around you. And this can be very, very relevant when you have millimeter wave or terahertz communications. Right. So what is the tricky part here is that you have to be very careful of how you design this antenna gain and this beam width of each of those sectors when you analyze the gain of doing this multi-sector BD RIS. And so you can compute the pass loss, and the pass loss would be a function of the gain of each of those RIS antennas. And what you can show is essentially that this is quite very intuitive. The gain here would be influenced by the number of sectors. So as you increase the number of sectors, essentially the beam width of each of those antennas would be narrower, and so the antenna gain of each of those RIS elements will increase. And so if you model this using different model of the beam width of the antennas, what you can show is that the amount of received power that you get with an idealized, beam patterns and more practical beam patterns, it will scale with the number of elements that we have in each panel, in each sectors, that's M. So the amount of energy that will be reflected by each of those sectors will scale with the number of elements that we have, RIS element that we have in each sectors. That's something we know already. But it's also a function of the number of sectors that we have in this multi-sector RIS. And what you can show is through those 2 figures, you have average received power versus the number of sections or the number of sectors that we have in this multi-sector RIS. And you see in red, this when you have an idealized beam pattern, and in black, when you have a really practical beam pattern. And so let's just focus on the black one because this is much more realistic. And what you see is that here you have the number of antennas for each sector is equal to 32. So the number of RIS element in each sector is equal to 32. And you increase the number of sections, the number of sectors. And so essentially, as you increase the number of sectors, the total number of elements in your RIS keeps increasing, right? And so naturally, your received power increases. What is more interesting is when you fix your total number of elements that you have in your RIS. So L multiplied by M is a total element, the total number of RIS elements that I have in this BD RIS. And so if I increase the number of sectors, the number of elements per sector has to increase in order to maintain the total number of elements constant. So this is what we have here in these figures. And what you see is that the received power keeps increasing as you increase the number of sectors. So in other words, if you want to maintain, if you have a fixed number of elements, if you use these in a 2D space, if you have 2 sectors only, or if you have 6 sectors, your 6 sectors would actually be more efficient than having 2 sectors. And so you have a benefit in having a multi-sector BD RIS in order to enhance the coverage of your application. And so this gain translate into a sum rate gain. Again, if you do multi-user mice, so you have a sum rate gain. And this is what you can see here, for instance, with the dashed lines. You have in red two sectors, so that's this hybrid mode. In black, you have 3 sectors. In green, you have 6 sectors. And so your sum rate increases with the number of sectors that you have for given total number of RIS elements that you have on your BD RIS. And so what's the 6th benefit of those architectures is that you enable a full space coverage for coverage sensitive application like millimeter wave and terahertz. Right, so the last structure of BD RIS I want to show you is the following one. So you know already this conventional RIS, where essentially every time you have an impinging wave is reflected by a certain element, and actually the reflected element, the reflected wave is actually originating from the same element. That gives you essentially this diagonal matrix. What you can come up with as well is an architecture where the incident wave is actually not reflected by the same element. So you can have an element here will receive an incident wave, and the element that will reflect the wave is actually another element. So it's, for instance, 2. So the energy comes from onto antenna 1 and actually is reflected by antenna 2. That's another architecture that you can enable with this. And that would also gives you a scattering matrix that is non-diagonal, and that's have some benefit. If you can change those connections, that would have some benefit as well. But you see here, the theta matrix is non-symmetric, and this may need to use non-reciprocal impedance networks, which may have other implications in terms of RF design. So that's another very interesting architectures of BD RIS, where you have this non-diagonal structure. So to conclude, what I showed here is there are some benefit to look at RIS architectures that are not restricted by diagonal matrices. And what we try to explore here is how you can make use of the off-diagonal element of the scattering matrix. And what we show so far is that one benefit is to be able to adjust not only the phase of the reflected wave, but also the magnitude. That leads to a boost in the received power and therefore a rate or sum rate. You can actually group those elements together in order to further boost the received power. You can decrease the number of resolution bits. So each impedance could have only 1 bit instead of having 4 bits, for instance. And it enables you this hybrid modes where you reflect and you transmit in a very efficient way. And the last architecture, which is really, I think, maybe the most promising, is when you have these really full sectors and full 360 degrees coverage very efficiently using those BD RIS. Now, there might be other BD RIS architectures that would be very interesting to explore. All the works here assume we have perfect channel estimation, so the channels are perfectly known when we design when you optimize the RIS. Channel estimation is obviously an issue. There may be other benefits of this beyond diagonal RIS, and there may be also very interesting applications to explore. So if you're interested, you can look at those very recent papers, and some of them are actually not even submitted yet. But with this, I would be very happy to answer any questions, and thank you for your attention.
So is there any questions on the floor or online? If you have, then please leave your chat. So we have the question. The first question is there any experimental prototypes of BD block diagonal RIS? Will it still be fully passive or require some power source?
Oh, well, there is no experimental prototype yet. So here, yeah, we haven't. So this is still at the, I would say, theoretical level. I think to prototype this, you need
quite a lot of expertise in RF design, so this is not something that we have explored so far, but that would be obviously very interesting. Right. What's the difference between channel estimation method of BD RIS and traditional RIS? Yeah, that's also an interesting question. So here what we assume, if I take the go back. So let me take this. So for instance, yeah, I mean, so you have those two channels, the channels between the transmitter and the RIS and the channels between the RIS and the receiver. So what we assume here is that we know those two channels, those two vector channels. And I think in BD RIS, you really need to know those two vector channels in order to do the optimization. If you have conventional RIS, maybe you could have some simpler channel estimation. Maybe it can leverage the concatenated channels that goes directly from the transmitter to the receiver, because each element of this diagonal RIS will actually impact just one of those channel gains. So there will not be this full-blown or full matrix theta that will really change one vector to another vector. So this is something we have really not exposed, how we could first leverage, you know, classical, I mean, channel estimation technique that we use for conventional RIS into the BD RIS, and whether we can do that, or we need to redesign new channel estimation techniques for BD RIS. That's, I think, a very important problem to explore. Right, so I missed some, there were many. Right, the intuitive benefit is the fact that, I mean, the really starting point is that because you have diagonal matrix here, where those diagonal elements are actually phasors with no magnitude equal to 1, you only control the phase of the incident wave. While here, you see the optimal theta would be a theta that actually convert a given channel vectors into a completely different channel vectors, where you don't only place on the phase of the diagonal element, but you play on all the entries of this scattering matrix. And so that's really have benefit in terms of in terms of boosting the power gain, but also in terms of enabling those kind of multi-sectors RIS, because those elements are now connected with each other. So that's really the benefit. In terms of architecture, is that each element is just connected to one load when you have conventional RIS, while here with the BD RIS, a given element is connected to other elements. Recording will go on to YouTube. Yeah, I don't know yet. Yeah. Thank you so much. Is connections between the sectors is lost. I don't see why it would be lost. It's really hardware connections. So I'm not sure it can be lost. It's not a wireless connections. Machine learning techniques in this area. So well, so I mean, we haven't not used no full-blown machine learning techniques, but actually when we designed the code book of those scattering matrices, or essentially the impedance network, we use some form of machine learning, the unsupervised learning based on k-means clustering. I mean, that's the furthest we have been in using machine learning techniques there. What if the element can be amplitude and phase controllable? Well, that's the whole point, is that if you have single connected architectures like here, the maximum you can get is actually
the maximum performance is by having each of those phasors will have a magnitude equal to 1. So if you have the magnitude will be smaller than 1 here. So if you control the magnitude so that is smaller than 1, you will actually lose in terms of received power. So the maximum you can do is actually having a modulus equal to 1 here. While here, you don't need to have these constraints. What you need is just that this matrix has to be unitary. So that's would maintain the lossless properties. But by having this matrix being unitary, what's happening to the reflected waves is actually the magnitude and the phase actually controlled. Right, so that's also an important question. So this matrix theta, so we optimize it using different techniques. One is you have these constraints, and so you can actually change your optimization problem such that you transform into an unconstrained problem, and you can use quasi-Newton methods to optimize your systems. Or when you have some rate, use other optimization techniques. But so far, we don't have a closed form solution to this problem here, for instance. Do I have a PhD student, Matteo, is close to having actually a solution to this problem. So that would avoid having any form of optimization, and you can have just a closed form solution, or actually a very simple algorithm to actually design this theta matrix optimally. Right. So I'm not an RF expert, but I know from my RF friends is this kind of architectures. This kind of architectures is really something that is very implementable using conventional RF design. The important bit that we try to do here is to impose this symmetry, because having reciprocal circuits in RF makes the design much simpler. But you could discard these constraints and make the circuits non-symmetric, but you may have more complex architectures. So I'm not sure exactly how the pin structure that you use in conventional RIS could be reused here, but I'm pretty confident from all the chats we had with RF people that this is really implementable with modern RF design. Right, active RIS. So yes, that's I know that there are a few people looking at active RIS. It's not something we have looked at, and that would be an interesting questions whether actually we can make it active. So you could imagine that, for instance, you take this multi-sector RIS here, and you make it active. So actually, you use this directly as a base station array. That would replace completely your multi-sector arrays, and you make it multi-sector using this kind of active BD RIS. Something to explore. We don't know this. I think that's it. Any other questions? Right. Yeah. So this is all narrow bands. Yeah, that's an important point also, is how you make it work for wideband application. And indeed, for millimeter wave or terahertz, you would have to actually enable this for widebands. Absolutely. Yes. Yeah, so this is something we have not looked at. But indeed, you may have additional constraints, especially if your RIS element there, you know, they're not frequency dependent. If your scattering matrix are not frequency dependent, then yes, you have compromise there between what's happening on one part of the band and the other parts of the band. Yeah, indeed. I'm not sure how much you could have, you know, frequency selective kind of scattering matrices or impedance networks. That's also something that would be interesting to explore. So it's interesting because you have to connect really microwave design and communication to do this. I think I missed one. What about mutual coupling between elements, a group of elements? Right, so that's what I emphasized at the beginning. So in all the analysis and all the architectures and the performance gain I showed you, this is assuming we have perfect matching and we have no mutual coupling. But if you have mutual coupling, yes, you can still use those RIS architectures. So that's not an issue, but then you need to start looking at other models. And your theta matrix is actually hidden within this complicated matrix, but you can still use the same architectures, but the performance would change, and the optimization of the theta matrix, the scattering matrix, would change because the channel model is different. Right. Any other questions? Yeah, I think it's the same. Well, if you look at the history of MIMO, people make it simpler by getting rid of the mutual coupling and saying we have half lambda spacing. You know, we know very well that actually those models are inaccurate once you start to pack antennas closer to each other, right? So here, if your RIS, you start having those elements that are, within half a wavelength, I think at some points, yeah, we need to start departing from those simpler model and try to capture this mutual coupling. And obviously, things get much more complicated. Yeah. Any other questions? And there is last one. Is hybrid IRS flexible to position of users? Right. So the hybrid IRS, yes. So it's the same as hybrid IRS or the multi-sector IRS. So you have this constraint. And so what's happening is that depending if you do sum rate maximization, for instance, and you have users on the left side and the right side of the IRS, those scattering matrix will be adjusted as a function of the quality of service that you fix for the users on the left side and the right side, and potentially as a function of the loads that you have on the left side and the right side. So dynamically, those scattering matrix would change as a function of the user location, density, the quality of service you want to impose on each of those users, and so on. And that would be the same for this hybrid case as for the multi-sector IRS here, where you have a similar constraint, but now you have L sectors, you have a sum over L of those terms. And so that would be adjusted dynamically, indeed, as a function of distribution of users, around the IRS. Right. I think that's it. Yeah.
Thank you for thank you for your the insightful new explanation for the RIS point the dimension for IRS design, and I also very thankful for the insights, the explanations for your research, and the answer for the questions. Okay.
Thank you very much, Namien.
Okay. Let's finish the lecture series. Let's dig in.
Thank you. Yeah, so feel free to send me an email if you have more questions.
Okay. In June, we will close the June. So thank you for attending the lecture series. And this lecture is recording. So the Professor Bruno will share the recording videos.
Put it on
and-
YouTube.
Okay. Okay. Bye bye.
Thank you, everyone. Bye bye.